So far we have completed our data preparation and our splits, and we have saved it in a DB kind using SQLite 3, and we have also completed our linear regression problem notebook, and the next model which you are going to see is ridge regression. So before that we need to know about ridge regression, right? So considering ordinary least squares, one key limitation is multicollinearity, right? So when our features are highly correlated, the least square solution can become unstable. So this will be like we will be having larger coefficient estimates. As we have large coefficients, our variances are also high. Our overall idea is to minimize the sum of squared residual error, but instead of doing that only, Ridge also minimizes the prediction error. Along with that, it will add a penalty to the proportional, adds plus a penalty proportional to the squared magnitudes of the coefficient. So we will be having a penalty term for the size of that coefficient, so that it will make it more stable and less prone to overfitting, because multicollinearity introduces overfitting because of the highly correlated independent variables, right? So what this regularization technique will do is, this regularization technique this is going to modify linear regression by adding just a penalty term. Okay, so here we will be saying it as L2 penalty, where lasso regression is called L1 penalty. So this penalty term, it is particularly used for data sets with multicollinearity. Okay, so this is then this works with an aim to reduce the model variance. So how does it do? Like how it reduces the model variances? It will not reject any kind of features away from the model, like away from the data. Instead, it shrinks the coefficients. Okay, it will not entirely eliminate it. So what this helps is, this will help the model to generalize better. Okay, so that it will be generalized well for unseen data. So the main idea is to find a new line that doesn't fit the training data as well. We will be introducing a bias instead of going with the complete SSR, minimal SSR. We will be introducing a bias for some at the cost of some training error. Okay, so in return of the small amount of bias, we get a significant drop in variance. So in terms of variance, we can say it is there will be a drop in variance. Okay, so ridge regression is a regularized extension of OLS that introduces an L2 penalty on the coefficient magnitudes. Also, this distributes the importance arm. So what this is, it aims to reduce the model variance by shrinking the coefficients while not entirely eliminating them. So what lasso does is, it will eliminate the features, but ridge regression will not eliminate. Instead, it shrinks its coefficient, so which helps the model to generalize better to new data. So it works on the basic assumption that all the features available in the dataset are somehow related, or somehow the cause for the output. So we are going to give equal importance to it, and by shrinking the coefficients, it avoids some particular features to dominate the model. Okay, so here our major hyperparameter is alpha. Ordinary linear regression, that is OLS, will use alpha is equal to 0, that is the direct minimum. And if we have larger alpha, the shrinker will be stronger, and if we have excessively larger alpha, we will get overfitting. So we are going to select, we are also going to see what ridge regression does for a for a moderate level of alpha value, and we are also going to see cross validation using RidgeCV and how it selects the best alpha from the given range of alphas. So here ridge is a closed form solution, and RidgeCV, so this is the kind of alpha range we will be giving. So what this RidgeCV will do is, it will take the training data set, It works with the alpha, evaluate the model, and then takes the training set, works with the next alpha, then evaluate. So this will kind of require n number of models. Okay, so from that alpha with low error, we can come to know that it generalizes well. So it selects it as a best alpha. So LOOCV is a basic concept, that is leave one out CV. That is, if there are totally n samples, LOOCV will take n minus 1 sample and the balance 1 sample as the validation. Okay, if we have 100 samples, it will take 99 as training set and 1 as validation set repeatedly. So this will leave one out errors are computed efficiently from the original fit. Okay, this is a closed form solution. And regularization, okay, improves stability under multicollinearity. Yeah. So because of that, we can even with a multicollinear situation, this will improve the stability. Okay, so this is ridge regression. Okay, we have our data ready. So our minimum date is 2015-11 and 2026. Okay, 21. Okay, no problem. Now we have our weather DB ready, and this is our helper function. So in the helper function, the major thing is load data, get linear pipeline, then save model, load model, evaluate model, visualize model, and get recent history, feature engineering, forecast next 3 days. So these are the things we have seen in the previous videos. So we are going to reuse the same, because Ridge is like nothing much more than this initial steps, but along with this implementation, we are going to see 3 to 4 specific visualization for this ridge regression. So first is going to be, so RidgeCV model diagnostics and regularization dynamics is the very like I got this sentence from like while browsing, and it felt more real, like RidgeCV model diagnostics and regularization dynamics. So these 4 visualization were tells us about the ridge regression completely. First is the alpha tuning curve, next is the cross validation error curve, then third is the coefficient shrinkage path, and finally feature importance bar plot. So these are the 4 plots additionally we are going to see for ridge regression, and the same for lasso regression. So now, instead of going deeper into this, first we will go and check with how RidgeCV and ridge works. So after that we will dwell into the visualization part separately. Now, so this will be our libraries, and from sklearn.linear model import ridge. So these are our libraries. This is our data loading. Okay, it will start load data. Okay, we have 3340 and 835. Now we are going to ridge alpha is equal to 1.0. So alpha equal to 1.0 is a reasonable reasonable alpha value, which is moderate, and is by default it is 1.0, and random state is equal to 42. We are going to keep the, we can also define the config we can also define the random state in the same utils, and we can call it everywhere, so that whenever we are partitioning, like whenever we are shuffling the data, it will be the same. So as of now I'll keep it. We need standardization for numerical columns and one hot encoding for the categorical column, that is the weather data. So we are going to call the ridge pipeline. So same as linear pipeline, I will have ridge pipeline is equal to utils dot, we have get linear pipeline method, sorry, function. So where we will pass xtrain and the ridge reg model object. Okay, spelling, oh god, I make spelling mistakes a lot. Okay, we have got for the numerical columns it is standard scalar, and for categorical columns it is one hot encoder. Okay, and our model is ridge with the random state. So we have the pre-processor step and the model. So we can also access model and pre-processor wherever needed from this steps of our pipeline. So next we need to unravel y train, right? So why are we unraveling it? Why are we raveling it? Okay, so this is called flattening y. So this will convert an array like object into a 1D numpy array. We'll see. So if I have around 3000 comma 1, okay, which will be samples and the features, right? So what our output will be after np.ravel is 3000 comma, so this is just n samples. So this will be our 2D column vector, okay, so which will be converted into 1D array. Okay, so this 1D array is expected by the scikit-learn estimators, and Ridge also expects the same. So we have to unravel it. Actually, we have to flatten it. Okay, so for that I have the code already. Okay, now we are going to fit, we have our x train and y train ready, so we will fit the data. Okay, so ridge pipeline, we have to fit the data in ridge pipeline, fit of our x train comma y train. Okay, we'll see. Now for the preprocessor we have numerical columns and the categorical column. This is our standard scalar, together it is under ridge. So this will be our complete pipeline. Okay, so we can have a detailed view of this pipeline. Okay, so what is in column, what is in preprocessor and what is under number and category, and what will be performed. Okay, standard scalar for the numerical variables and one hot encoder for the categorical variables. This is a detailed pipeline, and I think we can save this model, right? Utils dot save model. This is so simple to do. So I'll save the ridge pipeline, comma, we'll save it as ridge regression. Okay, so this will be saved, and for metrics we will move to our helper function, evaluate model, right? So in evaluate model this will return a dictionary. Okay, we will get it under metrics. Okay, and we can access it through model, RMSE and R2. So what can we do is ridge regression. Okay, we'll see. Okay, we have got the same RMSE R2 score as linear regression, right? Yes, our linear regression got 0.433 RMSE and 0.87 R2. Yeah, the same, like with little bit different, but it is the same. Yeah, like very minute difference, but this looks the same. Wow. Okay, so like obtaining the similar kind of RMC and R2 values of for both linear and ridge regression is not unusual to say, but it indicates that our baseline model is already stable and that multicollinearity may not be severe, right? So this ridge regression's primary purpose is like not to improve any kind of training metrics or something like that, but to reduce our coefficient variance, and with that we can improve our robustness and generalization, right? So I think we can actually, as this will reduce the coefficient variance, we can see the difference between the linear pipeline and ridge pipeline's coefficient. Let's see, we'll compare ridge pipeline dot under named steps I can access the model. So I mean this one, the named steps is equal to I can accept preprocessor, and with the model I can access the model. Okay, dot coef. Okay, along with this I'll also run linear pipeline. Okay, okay, I've run it. So let's see the difference. 7.3, 7.41. Okay, we have a reduced number here. 8.62 for linear it is 8.59, 2.7637, 2.7585. Okay, it is kind of similar but not much difference. Okay, but we have a difference in the coefficient like in the coefficient variance, right? So okay, it is good to get similar things, no problem. So next we have tried this with 1.0 alpha value, right? So what we are going to do is we are going to see RidgeCV regressor. So this is ridge regressor. And this will be RidgeCV. So as we have reused the same functions, there is no need of go through in the steps again and again. We can focus on the additional things that matters to ridge regression. So here I don't need the metrics. I can have RidgeCV directly from sklearn linear model. So here for alpha, we have mentioned alpha equal to 1.0, but for CV we need to give a space. We have to give a range so that in that space it can have 50 to 100 kind of different alpha numbers, so that in that log space RidgeCV finds the best alpha. So for that we can have np dot log space, and we can give 1 to 5 anything. So if you want 20 numbers or between 1 to 5 or 200 numbers, it is your wish, but this generalization is very much important, because alpha is the regularization strength, right? So this regularization strength, if my alpha value is 0, then there will be no regularization. It will look like linear regression. There will be no shrinkage, no changes. So if I have 0.01, okay, this will be very weak to see. So where this coefficient will shrink, but almost like ordinary least squares. So it shrunk, but we had a similar encounter with linear regression, right? So in such a way, if it is 1.0, it's a moderate kind moderate regularization, and more or less it is balanced one. If it is like, if we have more multicollinearity, high multicollinearity, and we have more independent variables that are correlated, so at that time this will act as a balanced regularization strength. And if I have 100, then it's the opposite, strong regularization. So the coefficients will shrink and it will become very very small. Okay, so these smaller coefficients makes the model like less sensitive to noises and the multicollinearity. So this will lead to more stable predictions and better generalizations on the unseen data, but it should not be very 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 minute and unnoticeable. It should happen, but this making this smaller coefficients, we can get better generalization. So that is also important. So introducing bias, like we are introducing this bias kind of thing, like intentionally, like this will be allowing, like we will be allowing a small increase in the training error. So at the cost of a small training error, we will be introducing bias, so that we can get a reduced variance. Okay, so reduced variance in the sense, if I say reduced variance, if we have an equation for our maximum temperature where 20 plus 0.5 of temperature change. Okay, so this is our final linear, like line equation. So if I have 1 mm of change, okay, there will be only 0.5 degrees Celsius change in our output. What if my equation is 50 temp? Okay, so this my prediction will be changed. Like if my prediction is 20 degrees Celsius, this equation will change into my actually prediction, like I'm expecting 29 degree or 30 degrees Celsius, but with this I'll be having more than 30, more than 40 additional, like 70 percentage, 50 percentage. So that kind of error is very much not appreciable. So this prediction changes, or like we need to introduce bias, so that these kind of variance issue, high variance issue, might be avoided. So our overall goal is reduced variance in compensation for the training error. Okay, now for that alpha, we are going to create a log space, np dot log space from -3 comma 2 comma 50. So I'm going to take 50 numbers in between, equally spaced between -3 and 2, and now I will be calling RidgeCV, where RidgeCV alphas, it will be alphas, and we will be storing our CV values as true. Okay, so we will fit it RidgeCV dot fit of I think we had the pipeline, right? So what we can do is, I'll erase it. We'll, instead of taking already fitted, already transformed X train, Y train, I think I can do this again, so that the naming, we can avoid the naming confusions. Okay. Okay. Now we can create alphas as np log space -3 comma 2 comma 50. RidgeCV is equal to RidgeCV alphas equal to alphas store CV values equal to true. So now we can create our pipeline. RidgeCV pipeline, which is utils dot get linear, the same. If for this we'll be sending our extrain CV and our model object. So the same. So there is a difference here. There is a difference here. See. Okay. So we can better see after fitting so that we can understand what has happened here. So why did we get that kind of a list? Okay, there is a difference, and we can see it in a bit. Now same as before, we will be using np.ravel to flatten y. The same, we are actually reliving the same thing. So now RidgeCV pipeline dot fit of, we have now extrain CV comma, I think, oh sorry, it's y train CV. Okay, it will be extrain CV and y train CV. Okay, now we can expand everything to understand where that thing came from. List of numbers here. So this is the alpha array. So here it was cut down because of the space. If we see here, we can see we have defined the log space between -3 to 2, I think, right? -3 to 2. In between it is equally separated from the range -3 to 2. We'll be getting 50 samples. So these are the different alpha values we have received. Okay, so after fitting, we have fit our data now. Now here we can get best alpha value and the intercept value for the equation. Okay, so first we will print the alpha value, where it will be RidgeCV pipeline dot named steps. From that I'll take model, from that alpha underscore. So this will be our best alpha. Okay, so I'll have best alpha, and also I'll also print the intercept value, the model that has found. Dot named steps, from model I can take intercept underscore. So best alpha is 12 and intercept is 28. So this is what RidgeCV is giving us as the best alpha and the intercept for our line equation. So now we can we have fit the data, so we can save the model RidgeCV pipeline as RidgeCV regression. Okay, now the metrics, the same metrics. Okay, this is the scatter plot between our predicted and actual. So this is where our some of the squared residuals are minimum in this line. So this will be our impact line and not our actual fit line. Okay, here this will give us the like how it is correlated to, or how it is like so much related to our independent variable, that is our temperature max. Okay, we have got all the features here, right? So this is our visualization part. This is done. Following this, we will do our forecast thing. So I don't want to waste so much time. So here are forecast results for ridge regression and not for RidgeCV. So we'll see if there is any kind of difference. Okay. So we got 29.84, 29.79, 29.76. So we already know, right? So this comes from the actual history, but this has one synthetic kind of data set which has one last input from its here, like which has a last input from the prediction, and the day 3 prediction is depended on two last prediction values instead of the actual history values. So this is, for me, this is less reliable, but I can rely on the first 2 days of prediction, right? So this is the forecasting of RidgeCV and ridge regression. So there is nothing new here, but one thing to understand is we are using the cross validation, right? So this RidgeCV will automatically select the optimal parameter, that is a regression alpha parameter, right? And this will refit the final ridge model on the what to say, on the like full training data set. Okay, we don't need to fit it again and again with the best alpha value. While doing so, the RidgeCV will automatically select the best alpha, and it will finally fit the model with that best alpha. So there is no need of getting the best alpha again and retraining the entire data set. Okay, so this retraining a separate ridge model is generally unnecessary. So unless needed, if we want, we can have, but the model object after fitting, this will have a trained model with the best alpha. So that is one pro tip for RidgeCV's regressor. So here this selects from this range of alphas. So this is ridge regression and RidgeCV regressor. So this is going to be the same for lasso, but additionally the next video will be on all these 4 visualizations. So this is going to be interesting because it took a lot of time for me to understand and look into the ways we can do the graph differently. So let's see how these curves turn out and why these are in the diagnostics. Okay, thank you.